So I'm going to start by considering a 1D analysis. In a semi-infinite domain. And I want to consider this same case that we considered before, but now instead of doing an integral analysis, I want to solve the whole thing. So I want to consider a wall that has some potential that's given by phi naught. And I want to assume that there's some bulk where this phi goes to 0 at infinity. I don't yet need to involve any of the fluid flow because, in fact, we already know what the relation is between the potential and the fluid flow. So I don't need to even bother solving that now. What I really need to do is I just need to figure out what is phi as a function of y. And so that's going to be our focus. Now, we want to take the same idea that we talked about when I first introduced electrostatics in a very simple way, and we want to apply that here. I said that in electrostatics there are really two key things that were important to us. One, when I have a source charge, what is the effect of it on its surroundings? And when I have a test charge, how is it acted on by the variation in the electric field? And we'll see that there's an analog in the way we're going to approach this problem. We're going to have two different relations that relate together: charge and the effects of charge, potential and the effects of potential. So we're going to take two different descriptions that relate charge and potential. First, we're going to take Gauss's law. That says that the divergence of the electric displacement is given by the charge density. If we write this electric displacement as the permittivity epsilon times E, and if we write the electric field as the minus gradient of that potential, we can then write this as a Poisson equation in this form. This just tells us that if we look at any point in space, the local Laplacian of this electrical potential is driven by the local charge density. And the one fluid parameter that affects that is the electrical permittivity. If our electrical permittivity is really high, then the presence of a charge has a relatively small effect on the local Laplacian. Right, and we said that electrical permittivity was a measure of the ability of the medium to polarize in response to a source charge. If I put a source charge in free space, it induces an electric field. If I put a source charge in the middle of water, 79/80ths of the effect of that is canceled by the fact that the water locally polarizes in response to that charge. So if I put a positive charge here, all of the little negative parts of the water rotate to cancel that out. And I'm left only with a small residual electric field that is 1/80th as big. And that's consistent with the fact that water has an electrical permittivity of 80 times the permittivity of free space. Okay, so this is Gauss's law. This is an electrostatic relation. We're going to combine this with a description that comes from equilibrium arguments. And we're going to write this Boltzmann relation in terms of the local molar concentration of ions in the system. That's going to tie back to charge, because if we know how many ions we have and we know what their valences are, the sum of all those will tell us what the local charge density is. But as a start, we'll write this Boltzmann relation in terms of the concentration of a species I. So if I write C, and C is denoting the molar concentration of species I, I can write this as a function of the molar concentration of these species in the bulk and the local potential energy that that ion sees. So this E is the molar potential energy. This T is Kelvin temperature. This R is the universal molar gas constant. And we can also say that R is related to the Boltzmann constant, which I'll denote as K sub B, and Avogadro's number, N sub A. So this argument of the exponential is basically a ratio between the molar potential energy that these ions are seeing at some location in space relative to the thermal energy in the system. And what this says is that if I have a very high potential energy state, E is large in magnitude, this becomes E to the minus big number, which means that these ions are very likely to be in that high potential energy state. The net result is that if I look at the concentration of those ions at a specific point in space, it's going to be proportional to how much there was in the bulk times a very small factor here. Now, in the system we're considering, I have some wall, and I'm assuming that that wall has some charge. That charge is leading to a potential being very different here than there. So if I assume, for example, that phi naught is negative, as will be the case in most microfluidic devices in most situations, I have a negative charge at the wall, and I have a negative potential at the wall. So if I take a couple of ions that are floating around in this electrolyte solution near these wall, what is the force that this positive ion feels relative to the wall? Is it attracted to the wall or repelled? It's attracted, right? So this positive ion wants to move towards the wall. This negative ion, in contrast, is repelled. It wants to move away from the wall. Right? Now, if I put a bunch of ions, a bunch of positive ions, and a bunch of negative ions, they will feel a repulsion or an attraction to the wall. Is it correct to say that every single positive ion will all be smashed up against the wall and every single negative ion will drift away to infinity? Everyone's saying no. Why not? What's that? Well, the electrical double layer is the result of the orientation of these ions. So you're arguing that they're shielding, and I think that's true, right? If I have a net charge here, I might have some positive ion moving in this direction, and at some point that positive ion will shield this negative charge. But let's assume that I have 5 units of negative charge here, and I have 4 positive ions there. Will all 4 of those ions be smashed up against the wall? There are not enough ions to completely shield it. But I'll argue that it still doesn't get smashed up entirely against the wall. Yeah?
Is it because the light repulsion of the positive?
So if we treat these ions as point ions, and if we treat the domain as a mean field continuum, then at that point we're ignoring those point-point interactions. And in that limit, that says that these ions, in fact, feel only an attractive force. Now, it is true that if you have lots and lots of ions, the ion-ion interaction becomes more important. It certainly becomes a lot more important when you have divalent and trivalent ions. However, we don't have to go to a situation like that to explain why these ions don't all get smashed up to the wall. And the key thing I want you to keep in mind is that there are other things that cause species to move around, right? If I had a passive scalar, and I had a high concentration of that passive scalar in one spot, right? So if I had a tub of water and I had a little blob of red food dye, the red food dye wouldn't all stay in one point, right? Because it would diffuse away, right? So I have an electrostatic force that's pulling this positive ion towards the wall, that's repelling this negative ion from the wall. But as soon as I have an orientation of ions where they're no longer uniform everywhere, I have a competing diffusive force, right? So that means that, yes, there's a force that will tend to make the positive ions move toward the wall, but they're not all dragged completely to the wall. There's a repulsive force that drives away these negative ions, but they're not forced to infinity either. There's an equilibrium distribution. At the equilibrium distribution, the electrostatic attraction is balanced out by the diffusion that is trying to smooth everything out. And that, in fact, is described by this Boltzmann relation. We'll go into the details of how that happens in coming weeks. What you'll find is that you can take the Nernst-Planck equation, which is the governing equation for transport of these ions, take it to the limit where it's not changing with time, and when you do that, you'll show that you can derive this Boltzmann relation. For the moment, I'm going to state this as a thermodynamic principle, that the likelihood of a thermodynamic state is, or the ratio between the likelihoods of two thermodynamic states is proportional to an exponential of the difference in potential energies normalized by the thermal energy. If the potential energy of the system is treated as electrostatic, right, we have a charge and it is at some location that has an electrostatic potential, we can then write this electrical energy, or this electrical potential energy E, in terms of the valence of the ion and the local potential energy. And so now I've written this molar electrical potential energy in terms of the electrical potential phi, the Faraday constant F, and the valence Z sub I. So my valence of species I is just the charge normalized by the magnitude of the electron charge. So if I, for example, had a sodium atom, its valence would be 1. If I had a sulfate ion, its valence would be -2. If I had a calcium ion, its valence would be +2. F is my Faraday constant. And this Faraday constant is the charge in a mole of electrons. Or to be precise, this is the magnitude of the charge in a mole of electrons. Yes?
So, is the concept of C, like this relationship, basically void for anything above 2? Because then you can't think of a point.
So, the question is, what's the validity of the concept of valence in this context? So let's talk about specifically what we mean by this context, and then we can go to directly answering your question. When I write this Boltzmann relation, this relation here, I am treating an ion as a thermodynamic state, which means that it stands alone and it means that it's a point charge. So I am taking the approximation where an ion, which of course has a finite size, and I'm treating it as an idealized point. Furthermore, I'm saying that it is a function only of a continuum field property, the electrical potential. And in that sense, this is a mean field continuum approximation. So everything about the Boltzmann relation is a point charge mean field approximation. Now the question is, when does that break down? Well, it breaks down as soon as the separation of the charges becomes small as compared to the BR lengths, right? And that ends up breaking down much, much faster when the ions have multiple or are multiply valent. So what you'll find is what we're doing here is really, really good for +1 and -1 charges. It's pretty okay for +2 and -2 charges at low concentrations, like below 10 millimolar. For triply valent, it starts being pretty bad pretty soon. But it turns out that most of our electrolyte solutions are dominated by monovalent electrolytes. And so this is quite applicable for the majority of our flows. Other questions? Okay. So I took my electrical potential energy per mole, and I've now written it in terms of the valence of an ion, the Faraday constant, and this electrostatic potential. Right? So I have a relation between potential and charge, and I have a relation between potential and ion concentration. All I need to do is I need to take this C sub I and turn that into a description of the net charge density, and now I'll have two equations and two unknowns, and basically now I can solve this system. So if I want to evaluate the net charge density of this system, that's given by the sum over I of Ci times Zi times F. This is basically moles per liter. This is charge per mole. So Ci times F is really charge per liter. Sorry, this is a number of, I'm just going to start again. This is moles per liter. This is charge per mole. And so this is now charge per liter if it's singly valent. The Zi now corrects for the fact that individual ions may have different valences. Zi also can be positive and negative, and so this accounts for the fact that I can have solutions with different, or I always will have solutions with ions of different charge. So if I have a 1 millimolar sodium chloride solution, that would mean that I have a millimolar of sodium, a millimolar of chloride. When I add this up, I'm going to take 1 millimolar times 1 times the Faraday constant plus 1 millimolar times minus 1 times the Faraday constant, and I'm going to get that the net charge density of this solution is equal to 0. And that will be true of all bulk solutions. Bulk solutions will always be electroneutral. However, right next to the wall, I can have a situation where one or more of the ions are disproportionately high in concentration because of this relation. And when that happens, when I add this all up, this rho E is now no longer going to be 0. So, from Gauss's law, which is electrostatics, the Boltzmann relation, written there and then again here, which is now equilibrium, point charge, and mean field. Meaning I'm not counting up exactly which ion is where, which ion is oriented in what way with respect to other ions, how is each individual water molecule oriented. I'm saying all these things can be treated with bulk macroscopic continuum properties. I combine Gauss's law and this expression of the charge density, and now I can write one equation for either the charge density or for the potential. And we find that it's much easier to do this for the potential. So I'm starting with Gauss's law, but I want to put something in for rho E, and so I'm going to put in this expression for the charge density. So for the charge density, I want to put in the sum over I of Ci, Zi, F. So I put in everything here except the Ci part. For the Ci, I'm now going to put in this expression. And this is the Poisson-Boltzmann equation. It's really just a Poisson equation where the source term is an exponential relation that describes the distribution of ions in the system. However, that exponential source term on the right-hand side is itself a function of this same parameter that I'm taking the Laplacian of on the left-hand side. It's a hassle for a couple of different reasons. One, it's a hassle because I have this sum. There's nothing complicated about the sum. It just makes things hard to write. And there's very rarely a clean way to describe what happens when you have 1 millimolar sodium chloride plus a 50 millimolar tris buffer plus 5 micromolar of calcium EDTA. There's just like no clean way to write that down. So in that sense, the sum is a pain. The other thing that's a real pain is this exponential term. By definition, it's exponential. That means that its radius of a convergence can be a real problem. If you try to simplify it, if you try to linearize it, if you try to describe it with a polynomial approximation, a lot of times it just doesn't work. The exponential function just gets big really fast. Right? And in fact, we'll find that if we start trying to solve this equation with any reasonably big potential at the wall, we'll find that the right side will blow up. The right side will blow up so badly that all of the approximations that went into deriving this equation quickly become incorrect. Yes?
So in many systems in fluidics, the wall is basically charged, but there is no potential in that field. In many, for example, any fluid instrument, you will have a surface charge associated with the wall. How does that relationship of surface charge transfer to
So I think what you're saying, and tell me if I've misunderstood you, is that the way the wall boundary condition is specified is by specifying the charge, not specifying the potential. Am I understanding you right? And then your question is, how do we relate the two? So we'll show how we relate the two coming shortly. In today's lecture, we'll probably get to a linearized description of how you relate the two when I can assume that the right-hand side is small and I can simplify everything. But in general, the relation is given by the Graham equation. And so the Graham equation gives a complete description for the relation between potential and charge. You are correct. When I talk about the fluid mechanics, I describe the boundary condition in terms of potential because it makes math really easy. And a potential is a good boundary condition for a surface that we call a Nernstian surface. And the problem is that microfluidic devices are not made out of Nernstian surfaces. So there's a disconnect between the practicality, which is usually that we know the charge better than we know the potential, but the math works out if I know the potential. But we'll link those two things together when we go to the Graham equation.
So when you say non-Nernstian surfaces, non-oxide-based?
Usually oxides are not Nernstian. Usually Nernstian surfaces are not the oxides. So the easiest way to make a Nernstian surface is usually to get some sort of crystalline halide.
What is the definition of Nernstian?
A Nernstian surface is a surface where the activity of the ions at the wall can be assumed independent of the activity of the ions in the bulk. So it basically works well if the thing that's driving the charge on the if you have a crystal, right? So if I had a crystal of sodium chloride, and it wasn't soluble in water, just work with me, right? The charge on that surface is really a function of the fact that you have tons and tons of sodium ions and tons of chloride ions. The exact details of how many ions you have in the bulk doesn't drive that. In contrast, when you look at an oxide surface, the charge determining ions on the oxide surface are driven by usually protons or hydronium rather than hydroxides. And you will find that the activity of, say, a silanol group or a deprotonated silanol group is in fact a function of the properties in the bulk. And because of that, you find then when the properties of the surface are independent of the bulk, you can write a very simple relation for the potential. In all these other conditions, you can't. In a certain sense, we're getting a little bit ahead of ourselves because now we're talking about all the details I would get into once I'm done with this.